Hi everyone, today we're going to learn about how to calculate equilibrium constant or equilibrium concentrations. Here's a page on the learning objective from College Board. You may want to pause the video and read it carefully. When we calculate K, we often set up an ice table. You might have heard of that before from your teacher. And the I's would represent initial concentration of the reactant or products given. The C represents change. And E represents equilibrium. And then we use a little bracket with a subscript of 0, meaning initial concentration at time 0. Practice problem number 1. For the reaction, iron 3 plus ion reacts with thiocyanate ion to make the complex ion FeSCN2 plus, which is red in color. Given that the initial concentration of the iron 3 plus ion is 1 times 10 to the minus 3 molar, the thiocyanate ion is 8 times 10 to the negative 4 molar, and the equilibrium concentration of the complex ion is 1.7 times 10 to the negative 4 molar. Find the value of Kc. Now, based on the stoichiometric mole ratio, it's 1 to 1 to 1. We can make use of that to deduce the changes. Because the equilibrium concentration of the complex ion is increased by 1.7 times 10 to the negative 4 molar, that means the concentration of the reactants, the iron ion and the thiocyanate ion, must be decreased by 1.7 times 10 to the negative 4 molar. So now here's the setup of the ice table, in which you have start with 1 times 10 to the negative 3 for the iron and 8 times 10 to the negative 4 for the thiocyanate. Now we take away 1.7 times 10 to the negative 4 molar from each of the reactant and add that amount to the product. And then we come to the equilibrium concentration for the reactant and products. Reactant being 8.3 times 10 to the negative 4 molar and 6.3 times 10 to the negative 4 molar, while the complex ion is 1.7 times 10 to the negative 4 molar, and we substitute it into the Kc expression, and we can calculate the value to be 3.3 times 10 to the power 2. In practice problem number 2, here we have carbon monoxide reacting with water to form carbon dioxide and hydrogen. The Kp is 0.0611 at 2000 Kelvin. Given initial partial pressure of carbon monoxide 1,344 torrs, and for that of water 1,766 torrs. Now find equilibrium partial pressure of all the species. Let X be the change in mole per liter. So based on a stoichiometric mole ratio of 1 to 1 to 1 to 1, as X is taken away from the reactant, is X added to the product. So now you have an ice table. Initially 1344 torr for carbon monoxide, 1766 for water, and nothing for the product. Now we take away X mole per liter from each of the reactant and add X mole per liter to each of the product, and we come up with equilibrium concentrations or partial pressure. Now we substitute that into the Kp expression, and we solve for the X by using the quadratic formula. X is solved as 305 torr, which is the partial pressure of CO2 and hydrogen at equilibrium. To go back to find the equilibrium concentration or partial pressure of carbon monoxide, we subtract 305 from the initial given pressure of 1344. We have 1,039 torrs. And for that of the water, we subtract the X from the given amount initially. We have 1,461 torrs. For practice problem number 3, 2 moles of hydrogen iodide decompose to form hydrogen and iodine gas. Now here's a diagram showing initially we have 1 mole per liter and eventually becomes constant at 0.6 mole per liter. And this is in a 1 liter flask at 800 K. calculate value of Kc, and plot the change in the concentration of hydrogen and iodine on the graph. So the graph shows that initially the hydrogen iodide was 1 molar per liter, but then it became constant, decreased to 0.6 molar. That means the change in the HI is 0.4, from 1 to 0.6 is 0.4. Now using the stoichiometric mole ratio, then the change in the hydrogen and iodine is 0.2. So we take away 0.4 from 1 mole per liter from the 2 moles of HI, and then we add 0.2 molar mole per liter to the hydrogen and iodine. Now we come up with equilibrium concentration of 0.6 for the reactant and 0.2 for each of the product. Now we substitute it into the Kc expression. And don't forget to raise that 0.6 to the power of 2. And we come up with Kc value of 0.11. Practice problem number 4. The diagram shows the initial and equilibrium pressure in a flask at a certain temperature for the reaction of methanol decomposed into carbon monoxide and 2 moles of hydrogen. So here's a diagram. Let's study it carefully. The figure 1 shows initial partial pressure of methanol, which is 1.2 atm, and then as equilibrium is reached, the total pressure now in the flask with the reactant and the product is 2.20 atm. Explain why the pressure will increase as the reaction reaches equilibrium, and calculate Kp. What would be the total pressure if the reaction goes to completion? Because the number of molecules of carbon monoxide and hydrogen formed as product are greater than the number of molecules of the reactant. So the increase of the number of molecules will create more frequent collisions with the container wall, thereby creating higher pressure. In solving for the K, for the X being the change of the concentration or the partial pressure of the reactant and the product, we start out with an ice table of 1.2 atm for the methanol and nothing for the carbon monoxide and hydrogen. Now we take away X being the partial pressure of methanol and add X to the carbon monoxide and hydrogen. We have 1.2 minus X being partial pressure of methanol and X for partial pressure of carbon monoxide, 2X being partial pressure of hydrogen. The total pressure is equal to all 3 species added together equal to 2.2 atm. Therefore, we can solve the X to be 0.5, which represents the partial pressure of carbon monoxide. And for the partial pressure of methanol at equilibrium is 1.2 minus 0.5, which is 0.7 atm. And for the partial pressure of hydrogen is 2 times 0.5, which is 1 atm. If the reaction goes to completion, all that methanol would totally decompose. Therefore, we use stoichiometric mole ratio of 1.2 atm for the partial pressure of methanol, converted into 3 moles of product, mole ratio of 3 to 1. And then we end up with 3.60 atm for the total pressure at the end. That's all totally due to the formation of the product. To summarize what we have learned today, students have learned to use the ice table to calculate equilibrium constant K given the initial or equilibrium conditions from data or graphs. And we learned how to use stoichiometric mole ratio and the law of mass action to determine qualitatively and or quantitatively the condition at equilibrium for a reaction based on initial concentrations or partial pressure and the equilibrium constant. From the team of MLCA, we would like to thank you for watching our video, and we look forward to seeing you again next time.